deposit was contaminated with lead from uranium decay. So that was quite obvious, and you can see those results down in the bottom left-hand corner there. But we also found that the soils up to 20 miles away, their lead concentrations plotted on an isochron line that lined up with the lead from the uranium deposit, which of course is absolute nonsense, absolute nonsense. So it just shows you that, in that case, the soils had obviously been contaminated by all the rocks that they were sitting on, and the age had nothing to do with the true age of either the soils or the rocks. Here we have some granites in southeastern Australia, where you can compare the neodymium isotopes and the strontium isotopes, and you actually show that the granite formed as a result of mixing of the isotopes from different sources of rock that melted to form the granites. So the isotopes again have nothing to do with the age. They have to do with other processes that have affected the parent-daughter relationship, in this case violated by crustal contamination. Everywhere we look, there's evidence of crustal contamination. So that violates the second assumption. And the third assumption, of course, is constant decay rates. Okay, constant decay rates. Now again, in the Grand Canyon, I said we have a number of rocks that we investigated during the rate research program. Go to the bottom of the Grand Canyon, you've got in the crystalline basement rocks, you've actually got metamorphosed basalt lava flows that are now called amphibolites. This is what they look like down at the Colorado River. They're a black rock like a basalt, but under heat and pressure they've been converted into a different rock with different minerals. And they're very common. In fact, in this photograph you can see to evidence, you can't quite see it because I've got a better photograph I should have up here that's got a marker on it. But if you see that label down the bottom, there's differences in that outcrop that indicate the bottom and top of the original basalt lava flow. It was originally horizontal, of course it's been tilted up vertically now, but you can see the top and bottom of what was originally a horizontal lava flow. These are basalt lavas. So how old are these amphibolites? Using the isochron dating method, we got a rubidium-strontium age of 1240 million years on 19 samples. Notice that? Not 4 or 5 that they usually use, the geologists usually use. Remember I said we went for overkill? 19 samples. Samarium neodymium, age of 1655 million years on 21 samples. And we got a lead-lead age of 1883 million years on 20 samples. Now, even with those error margins, those ages do not overlap. The plus or minus in the brackets is the error margin from the analytical error in the chemical analyses. And you can see there that none of those two ages agree, none of them overlap. They are distinctly different from one another. How is it that these three different methods on the same rock samples give three entirely different ages? If you go to the geological literature, they would argue that no matter what method you used on a rock, it should always give you the same age. That's why they usually only date a rock with one of these methods. They don't normally spend the money to do more than one method on the same rock. And so we deliberately, in this research program, chose to analyse each rock sample by more than one method to see whether the methods really did agree, whether the clocks had all ticked at the same rate in the past. So just to show you how we plot that, there's the isochron, the rubidium-strontium isochron. There's the samarium-neodymium isochron. And this is the lead-lead isochron. And for those who are coming to Pittsburgh next month for the 6th International Conference on Creationism, I'll be presenting a paper on this in much more detail, a technical paper. This is what happens when you hit buttons. So when you plot these results on a diagram, down the bottom is what we call the present half-life. That's the decay rate, the measure of the decay rate. So uranium has a faster decay rate than rubidium, and samarium has an even higher, a slower decay rate. Okay, uranium decays faster than rubidium, which decays faster than samarium. And look at the differences in the ages. You can see that even with the error margins, they do not overlap. Why is it that these three methods should give such vastly different results? So we also found that the potassium-argon individual sample ages, that is the model ages, varied widely. In fact, in one outcrop, two individual samples from the same original lava flow, only a little more than 2 feet apart, one gave an age of 1,205 million years, the other 2,574 million years. Here's the outcrop, and we're looking at that dark rock in the middle of that gully. Okay, in the centre of one sample gave an age of 1,205 million years, less than 2 feet, just over 2 feet away. In the same outcrop, in the same original basalt lava flow, an age of 2,574 million years. Well, let's look at another. We mentioned the Cardenas basalt earlier. It's down in the bottom layers of the Grand Canyon. This is what it looks like from the south, from Desert View Tower. Those black rocks in that cliff there, they're all basalt lava flows. Here they are, up close and personal, and there's Steve in there, Steve Austin. We're in there collecting samples for this work. What kind of results did we get? We got a potassium-argon isochron age of 516 million years on 14 samples. The rubidium-strontium age I referred to earlier on 19 samples of 1,111 million years. Now notice that. The rubidium-strontium age is more than twice the potassium